Welcome to the iGetChem channel where we help you learn chemistry by showing you how to do problems. Um, in this video, we are going to look at a problem which is quite typical in an equilibrium calculation, where the objective is to calculate the equilibrium concentrations of all the substances in a reaction where you're given information about the initial conditions. So I'm going to read the problem, and you're welcome to pause and look at the problem in greater detail before you check out the solution. So the problem says the equilibrium constant for this reaction, which is 2N2O5 gas going to 4NO2 gas and 1O2 gas, is 1.3 times 10 to the minus 6. If N2O5 with an initial concentration of 1.000 molar is allowed to react to equilibrium, calculate the equilibrium concentrations of all three species. As we have said, this is a fairly typical equilibrium concentration calculation. And so let me summarize what we know from the problem to set up the solution. So first, let's write down the equation for the reaction. The equation is 2N2O5 going to 4NO2 plus 1O2. So as always, you will need the balanced equation in order to do any equilibrium problem. So you need to check that this is already balanced. If not, you need to balance it. So this particular equation is already balanced. So what we can first do is to write down the equilibrium expression. So the equilibrium constant K is equal to the product concentrations, so NO2, to the exponents given by their stoichiometric coefficients. So we see a 4 in front of NO2, so NO2 concentration raised to the 4th power, and O2 concentration raised to the 1st power, and the N2O5 being the reactant goes into the bottom, and it's raised to the power 2. So you see that these coefficients right there, 2, 4, and this implied 1 goes into the exponents in the equilibrium expression. It turns out that the problem really doesn't tell you that this is Kc, Kc being the equilibrium constant defined in terms of concentrations. But since the problem talks about concentrations only, we will assume that it is Kc, and the problem gives you the value for that equilibrium constant being equal to 1.3 times 10 to the minus 6. So before we set up the calculation, you can see that the value for this equilibrium constant is quite small. What that really means, because the equilibrium constant is essentially the product concentrations over the reactant concentrations. So if the value for K is really small, it means that the numerator for this expression must be small compared to the denominator. And because of that, you can understand that the extent of this reaction is actually quite weak. So if you look at the value for K, it being that small indicates that the extent of the reaction lies very far to the left. So what that means is that the reaction favors the left side of the equation, which are the reactants. So with that, we can set up the calculation. The easiest way to do this calculation is by what we call the ICE table. And if you are not sure how to set that up, you can check out another one of our videos on the channel. Um, but let's assume that we know how to set that calculation up, and we're going to first draw a table for the three lines we need in the ICE calculation. So I'm going to just put my table down. And there are three lines to this table. The first line is I for initial. The second line is C for change. And the third line is E for the equilibrium value. So we're just going to draw a double line to separate the reactants from the products. And so that's our IC table. So the IC table helps us sort of organize our numbers in a more visual way. So in order to start the calculation, we will have to figure out what to put down into the equilibrium values, into the initial values for the concentration. So the problem tells you that initially you have 1.000 molar of N2O5. It doesn't tell you anything about the two products, so we will just assume that they were 0. So initial value for N2O5, 1.000, 0 and 0 for the two products. Now, to calculate the actual equilibrium concentration, we need to figure out what change would the system actually undergoes in order to come into equilibrium. And we don't actually know that change at this point, so we will have to represent that change using an unknown value x. So we'll just put x, x, and x. Now, in this case, we know that since we started with no products, so you notice that in the first line of the table, you only have reactants but no products. So in order to arrive at equilibrium, the reaction has no option except to move to the right. So the direction of the reaction is indicated by this arrow. And so as a result of that, we know that to approach equilibrium, then the reactant must decrease, whereas the products must increase as the system moves towards equilibrium. So based on that, we know that the sign for the change in the second line would have to be negative for the reactant, but positive for both of the products. Because the product concentration goes up, the change must be positive. And finally, we need to include into this into the changes the proper stoichiometry of the reaction. So we notice that there is a 2 in front of N2O5, so we pull that down and put that in front of the unknown x. There's a 4 in front of the NO2, so we bring that down to the second line for the change of NO2. And we see that there's a 1 there, so for O2, so we put that 1 there. So now we know that including the signs of the changes as well as the stoichiometric coefficients, the change in the concentrations for the three substances are minus 2x for N2O5, plus 4x for 4NO2, and plus 1x for the O2. So now finally, to write down the equilibrium concentration, we would just apply the change to the initial concentration. So what that means is we will just add line 2 to line 1. So here we have 1.000 minus 2x Here we have 0 plus 4x, which is just 4x. And for O2, we have 0 plus 1x, which is just x. So these are now the equilibrium concentrations in terms of the unknown x. And if we put them back into the equilibrium expression, then we can use that equilibrium expression to solve for the unknown value for x. So let's do that. So k is equal to 1.3 times 10 to the minus 6 is equal to the NO2 concentration to the fourth power. So that's 4x, which is right here, to the fourth power, multiplied by the O2 concentration, which is right there, x, to the first power, divided by the N2O5 concentration, which is that 1.000 minus 2x to the second power. So at this point, I like to remind my students that you should watch the, to make sure that you have the exponents correctly written in the equilibrium expression, as well as the correct coefficients in front of x, because they appear several times. It's easy to miss some of them very often. So if you then expand everything, you notice that on top you have 4 to the power 4 multiplied by x to the power 5, and in the bottom you have 1.000 minus 2x squared. So you notice that I haven't expanded that, I just left it as that. I'll explain why in a second. So a lot of students at this point, because every time they see an Icy table, they thought they would have to use a quadratic equation to solve it. In this case, that is actually not correct, because if you look at this equation, you will see that the equation has a fifth power of x. So the quadratic formula can only solve quadratic equations, and quadratic equations are equations whose highest power in x is 2. So in this equation, you have x to the fifth power, and that definitely cannot be solved by the quadratic formula. So in order to really figure out this problem, you need a different strategy. The quadratic equation and the quadratic formula will not work in this case. But in this particular problem, we noticed earlier that the value for the equilibrium constant, 1.3 times 10 to the minus 5, is very small. And because of that, we said that the extent of the reaction lies far to the left. What that means is that when the reaction actually reaches equilibrium, the change to the concentration of the reactant isn't very much at all, because the reaction lies far to the side of the reactant. So in that case, we suspect that whichever this change to x actually is probably very small compared to the initial concentration. So if the initial concentration changes by a very small amount, then we can perhaps assume that the equilibrium concentration of the reactant is just very much the same as the initial concentration, because it doesn't change that much when it reaches equilibrium. So we are going to use that approximation, because without that we really cannot solve the equation anyway. And second of all, the value for the equilibrium constant indicates that the extent of the reaction lies far to the left. So we're just going to make that approximation. Now, whereas we can make the approximation that x is very small compared to 1, we cannot make the approximation that 4x is small compared to 0, because 0 is nothing. Whichever x is, no matter how small it is, it's still a significant number compared to 0. So while we can use that approximation that x is small for the reactants, we cannot do that for the products. So what that means is that the value for the equilibrium concentrations of NO2 and O2 must still be represented by 4x and x. And now if we apply that approximation to the bottom, to the denominator, then you see that I can simplify this expression. So instead of doing equal, I'm just going to do approximately equal to 4 to the 4th power, x to the 5th power, and now the bottom is just approximately 1 squared. And you see, that's why I did not expand this, because I was going to make this approximation, after which the denominator simplifies and the x disappears. So if you write everything out, 4 to the 4th power is 256, and this is just x to the 5th, and 1 to the 2nd power is just 1, right? So it simplifies to essentially 1.3 times 10 to the minus 6 is just approximately equal to 256 x to the 5th power. And now, since that equation only contains 1 x to the 5th power, you can that equation is really easy to solve. So let's solve that. So I'm just going to go to the left. So if I put everything together, I see that this is 1.3 times 10 to the minus 6 divided by 256, and that's equal to x to the 5th power. And so what you can do is to just put the left side into your calculator, and you can then take the 5th root of that, and you will get the answer. X is equal to 0.0219. So that is the solution for x. Now you remember that this x really isn't the exact solution. It's the solution obtained by making this approximation. The approximation is to replace 1.000 minus 2x by 1. So this is not really an exact answer, but it's only an approximate answer. So I'll emphasize that by this wiggle. So x is approximately equal to 0.0219. And so if you had used that, then you can calculate the final concentration. Simply, the concentration of N2O5, according to our approximation, is just about 1. But the final concentration for NO2 is 4 times x, and that turns out to be 0.0876. And the concentration for O2 is just x, and that is just 0.0219. Okay, so these are the answer for the concentrations of N2O5, NO2, and O2 at equilibrium. So let me just box them. So there is one final thing that you really should do, which is to verify, in fact, that whichever approximation that you've made to arrive at the answer is a legitimate approximation. So to do that, we need to figure out how is the approximate value that we assume for N2O5 compared to the actual value that you would get with the right answer. So remember, the approximate answer is 1.000, but the actual answer should have been 1.000 minus 2x. So if you put this value of x equals to 0.0219 into this, so let me actually just write that down. Then you see that the more accurate answer for the true equilibrium value of N2O5 turns out to be actually just 0.956, whereas the approximate answer, or the approximation we assumed, was that this was very close to 1. So the question is this really approximately equal to 1? And to evaluate how good that approximation is, we often use what is called the 5% rule. The 5% rule is basically asking, are the two answers, that is the approximation versus the actual answer, are they within 5% of each other? And so the way to do that is that you take the difference and you ask, is the difference between these two values less than 5% of the actual value? So we are really asking whether the difference, which is, so delta is the difference between these two answers. So the approximate value minus the actual answer. So we're going to just use an absolute value. The absolute value is whichever it is, whether it's positive or negative, we will just use the amplitude. And we will take that and divide that by the actual number. So of course, the difference between them is just 2 times x. So that divided by 0.956 turns out to be 0.0458. So this is about 4.6%. So what that means is that the approximate value we use for N205 is 4.6% away from the actual value. And that is less than 5%. So according to the 5% rule, that would have been an acceptable approximation. Okay, so this is the solution for this problem. And if you haven't checked out some of our other videos on how to do IC calculations, and some of them would involve using the quadratic equation for reactions where the highest order of x that shows up in the equation are no larger than 2, then you should watch those videos. And finally, if you like this video, please subscribe to the channel and give us a thumbs up.